7.2 Applications of Newton's Law of Gravitation and Cavendish's Experiment. Worksheet do number 5 and 6. And if you want to do number 8, if you want to try, you can. All right. 7.2. First thing, you can read this on your own. I might mention it and talk about it in class, but it just says Newton came up with the law of universal gravitation that we show you. I've shown you the equation, the force of gravity. Now, he did not know the constant g. I like to call it ma/mb over r squared. But he knew this part was right. He just didn't know what the number was there. Now, it says that, yeah, as we said, that any two objects will attract each other by a force of gravity. In 1731, an English scientist, Henry Cavendish, he's also a chemist that discovered hydrogen gas. He conducted an experiment to calculate gravitational constant. Now, what he did was, it's interesting, and there's a little, it talks about it here at the bottom of this page, the Cavendish Experiment. And there's a little diagram of what it looked like. He used, imagine they're like kind of like bowling balls, but they're lead spheres, like bowling balls and some smaller bowling balls, lead and smaller lead balls. But what he did was he attached them to the center of a rod, and he hung it suspended it from the ceiling. Can't do too great of a job trying to draw this. Almost like weightlifting, or like the old pictures they'll show you, like the dumbbell they would call it or whatever. But they were hanging these two lead spheres, and then what he did was he used a very thin wire. This is lead, really heavy metal. Then, well, these were both the same size, large masses of lead. But then he put two smaller masses, and this was a thin wire that he would be able to see. Like, imagine like on a wire, like if you twist a wire, you'll be able to see how much, the curve that it made in the wire. He wanted to know that as well. He wanted it to be able to rotate, and what he did was, he put two smaller spheres, like one here and one here. And the idea was there will be gravity between these two spheres and gravity between these two spheres. I don't know where he put those. Probably they were from the ground. They were probably they were probably set up from the ground up to try to attract these. And he put them in a room where there was no air moving around, it was still air, to see if these things could attract to each other. And they actually did. He also put a light beam. I'm not going to ask you to describe this. I'm trying to remember it myself and see it. He had a light beam he shined on to a lead sphere. And then, when you shine a light, he put some mirrors on it on one side. Let's just say if he put a mirror there or a mirror there, and he had a light beam shine there, and then the light reflected somewhere else. That was just so he could tell if that light moved. Like it was in a dark room, so he saw where the light was reflecting, and he marked the places where they were at the very beginning. Then he put the spheres there and let it go. And then when they were attracted together, he looked at where the light beam moved to. Because it was probably a very small amount of motion that happened there. And let's just see what it says here. He arranged the two large lead spheres in fixed positions at a close distance to each of the lead spheres. He observed the gravitational force did attract them between the small and the large. So the small and the large attracted. And here the small and the large attracted. And it caused it to rotate. This was hanging from the ceiling. And then what he did, this is stuff again beyond what I'm familiar with how to do this, but he was able to figure out the force required to twist that metal. When that was equal to the gravitational force, the rod stopped rotating. So the metal was only going to be able to twist a certain amount and then it wouldn't twist anymore. So he used a thin metal. I guess he had practiced this sometimes and said, okay, it'll twist like 3/4 of a turn, but then it will not be able to move anymore. It won't budge because it's just too tight. Too much force needed from it'll be greater than with the gravity. He wanted to see what the maximum attraction force could be between gravity. What's the maximum force you could get between these two? And so he based it on how far it would twist it. If he had allowed them to just come in contact, he wouldn't have known the maximum. So that's a neat experiment. And he was able to use the light. Well, anyway, so he calculated the gravitational constant 6.67 10 to the negative 11 Newton meter squared over kilogram squared. Okay. Now, what I'm fascinated and amazed by of this is that he was able to. This experiment, lead spheres attracting to others, hanging from the ceiling, mirrors and a light beam, coming off of them, twisting a wire. That's stuff that someone could have told that to Newton. They had all those materials in Newton's days, but Cavendish was about 150 years. What did I say it was? Did I read that? 1798 he did this. And Newton had been, like 150 years before that. So it's amazing. So I just always said that Cavendish experiment, that was an important one. But if they could have figured that out during Newton's day, they would be farther ahead now, probably even in what we know, technology or astronomy at least. Okay, so now, once they knew this constant, suddenly they were able to calculate the mass of the Earth. Like the very next day, imagine, they said, oh, Cavendish found out the gravitational constant. Look, it worked with all the data. Oh, we can now find out what the Earth's mass is, and here's how you do it. And there's a problem A right there, and I'll show you this. It says, assume the Earth is a perfect sphere. If it were, it would have a circumference of 4.01 10 to the negative 7. So it would be this all around the Earth, if it were a perfect sphere, would be around the equator, whatever. Circumference 4.01 10 to the negative 7. No. 10 to the 4.01 10 to the 7th meters. Okay. Now it says, calculate the mass of the Earth. Hint, imagine a person were standing on the Earth. Okay? So let's just say the Earth is going to be object B, mass B. Now, the other thing we would know is let's use a whole person. We can use her, Lily, and we'll let her be, she'll be A, mass A, and we'll say her mass is 25 kilograms. So she's going to stand on the Earth, and we're going to use her to calculate the weight of the Earth. Now, what you would also need to do is this. We know MA, we already know that if she's 25 kilograms, that because the Earth is 9.81 gravity, we would know this. And they would know this too. They would know all this information. 245 newtons. That is her weight. So, her weight, 245 newtons, would equal the gravitational constant, which is 6.67, 10 to the negative 11. Okay? And then we said it was Newton meter squared, kilogram squared, if you care to have that all there. Times the mass of A is 25 kilogram. The mass of the Earth we don't know, MB. And the only other thing we need to know is, what is the radius of the Earth squared? Okay, well see, imagine, that in the day that this was discovered as well, that there had been, before Cavendish, before that year, there had been many scientists or explorers had gone around the world. Who was the first one to go completely around the Earth? Was it Magellan, or I can't remember who the name was, but imagine if you go on the equator all around the Earth, then you would know that's the circumference of the Earth. Well, Newton also would have known that circumference of the Earth is 2 pi r. that he can find the radius of the Earth. So that radius would be from the center to the outside or the center to the top. It'd all be the same if it were a perfect sphere. And you can imagine that it will be okay. It's a good estimation. So the circumference of the Earth is 4.01 10 to the 7th equals 2 times 3.14 is pi times r. Sorry, I'm running into this problem here a little bit. But let's do this to find the radius of the Earth. So 4.01 10 to the 7th divided by 2 divided by 3.14 gives us a radius of 6.39 10 to the, oh boy, 1, 2, 3, looks like 10 to the 6 meters is the radius of Earth. All right, let me see if I've got, I didn't write it down in there. You'd have to, yeah, we just figured it out from the circumference. Okay, so 4.01 10 to the 7th divided by 2 divided by pi. And then 1, 2, 3, yeah, 6.38. 6.38 10 to the 6. I put 39. Okay. So we know the rate. Why do we care about the radius? Okay, you might see that for a minute. We have to know, why is that radius this radius? Because yeah, if she's standing on the Earth, I can't really draw. Well, I'll have to draw another picture of her up here. I guess I'll put her up here. We got the circumference already. If she's standing up here, well, she's pretty big, isn't she? Okay. Then between her mass and the mass of the Earth, that will be the distance, the radius. Now, technically, the radius is here, and you have to add half of her height. But that's so small compared to the center of the Earth to you. From the center of the Earth to you is pretty much how far you are from the center of the Earth. I mean, that's it. I mean, that we can add on a little bit of what her half her body height would be to her center of mass. You know, pretty much around that. But there's no need to put that. It'll be insignificant. Okay, so we'll plug that in. 6.38 times 10 to the 6 meters. Now, the meters squared will be squared. They'll cancel out there. The newtons over here will cancel here. The kilograms here. Well, actually, 1 kilogram will cancel out, but then your answer will be in kilogram. We're trying to solve for mass of the Earth, B. So here we go. A lot of crazy math. Actually, the only really crazy thing is this one. 6.38 10 to the 6. You got to square it. And when you square that, it becomes, well, I can write 25 MB over 4.07 10 to the 13th power times the constant 6.67 and then 245. I'll take away this part. You've already got it. So we just use FMA or FMG to find out what her weight is. And her weight is what the Earth is pulling on her. The force the Earth is pulling on her. Well, remember, if the Earth is pulling on her with 245, she's also pulling on the Earth with 245. But that 245 is a very small number. It's actually like 55 pounds. So if you pulled 55 pounds on the Earth, the Earth is so heavy you're not going to do much changing of that. All right, so 245. So we're solving for MB. I could have gone back up here and called that M Earth. And that would be M of the little girl, A, but oh well. ME, if you'll call it ME or M Earth. So let's calculate that. So 245, sorry for the messy writing there too. First, 245 divided by, well, if you want to do it first, divide by 6.67, 10 to the negative 11. Then multiply by 4.07, 10 to the 13th. Then divide by 25. And it looks like I get from doing this 5.97 times 10 to 20, 5.98 10 to the 24th. So 5.98 10 to the 24th kilograms is the mass of Earth. Now, based on that data that they would have had, all of that in that day, even in Newton's day, they would have had all that data. He just didn't have the G. But based on that, the real Earth mass is 5.98 10 to the 24. Oh, no, I'm sorry. Hold on. I did get 5.98. The real mass is 5.98. I thought, okay, yeah, I got the answer then. It tells you there on the paper, 5.98. Real mass, 5.98 10^24. Yeah, it turned out to be correct based on the data given. All right, pretty neat. So what that also tells us is they have other ways to figure this out now, like the mass of Mars, for example. But like if you could go to Mars, if you go to an unknown planet, or an unknown planet, astronauts one day could go to an unknown planet, they land on the planet. First thing they can do, they know their own body weight, okay? Actually, they can put a scale down and weigh. No, they have to weigh what it will be on that planet. Sorry about that. They get a scale and they say, okay, on this planet I weigh, whatever, 245 newtons, or I weigh, 800 newtons on this planet. They'll know their weight. That will be that will tell them the force of gravity pulling on them. Then they have to know their mass in kilogram. That's easy. If you know your weight, you would know your mass anyway. You can figure that out. Weigh it with a balance. Then they would need to get on some kind of like a car or rover or whatever, or if they rode it on a plane or rocket around it. They have to find out what is the circumference of that planet. So they got to go all the way around the planet, all the way, and measure the circumference. When they know the circumference, they can find the radius, and then they can plug it in, and they'll be able to figure out the mass of that planet. Pretty neat. Pretty neat. All right. Now, there are some other things. Once Cavendish figured out this constant, and they were able to verify and find the Earth and all these calculations, then they were able to do some other calculations as well. And there's a little section here in the notes next about orbits of planets and satellites and Newton's thought experiment. I think I'll wait and talk about that when we do a live lesson instead of doing it here. I want to get to the math part. But there are a couple of equations that can be derived. And one of them is they combine. You don't have to worry about doing this, but you might recognize this as the Centripetal Force equation. Remember the mass, and it says 4 pi squared r over period squared t squared. Remember that one? We did earlier in this chapter. And then they also take force as mg, weight, and they take Newton's equation that I just showed you on the board. So this one, along with F equals mg, along with the acceleration, is equal to 4 pi squared r over r squared. Acceleration, centripetal acceleration. And they took all those. You're not going to have to do it. But they combined them, and they came up with 2 new equations from that. One of them looks like this. They're actually down in the section that says orbital speed. So I was putting the derivations of those in there, but it turns out you really don't have to worry about deriving them. But I'll write it here. One of them is this. V equals the square root of g mc over r, and I'll explain what this is in a minute. The other one is t equals 2 pi, the square root of r cubed over gmc. Okay, so here's what this means, these 2 equations. One is for the orbital velocity, speed. Orbital velocity. We call it orbital speed. I know we really better call it velocity. And this is orbital period. Now, what it means is this. So let's just say that you have a planet orbiting, or a moon. Well, it doesn't matter where it is. It could be anything. We'll just say this object is going around C. Now, that's the central body. C means central body. So this goes around the central body. I would need to know the radius. The orbital radius would be from center to center. All right? And I can figure out from this now an easier way to find out what's the velocity of that moon going around the planet. Or if I know the period and so forth, I can find the radius out. Pretty neat. So based on the period, if I know the period and I know the mass of that body, I can also figure out the radius, or vice versa. If I knew the radius and I knew the period, I can figure out that. So period, radius, mass of central body, velocity or speed of the satellite times the mass of central body. Mass of central body and the radius. You can link all those together. Just kind of convenient equations, kind of neat stuff. So let me do. I think the best problems are D and E. Calculate the period. I could do it here on this part of the notes B and C, but I think it's kind of redundant and wouldn't be necessary. So I might need some data from that question. We'll see. So let's go to letter D. We're going to skip all the way to D. I'll do this one first. It says, because your homework looks like the ones I'm doing. So, but I think you'll be able to do the other ones as well. It says, assume the satellite orbits Earth 225 kilometers above its surface. So this is 225 kilometers above Earth. Now, first of all, when I see 225 kilometers, I'm going to immediately turn that into meters. Because all these equations require meters. Uh-oh. So, 225,000 meters above the Earth. So 225,000 meters above the Earth is a satellite going around Earth. Okay? Now it says the radius of the Earth, 6.36 10 to the 6 meters. I guess it's a little bit different than what we had before. Okay? And then it says the mass of the Earth, 5.97 10 to the 24th kilogram. So the first question is, number one, calculate the orbital speed of the satellite. So this is pretty easy. It's just that the questions look yucky, but they're pretty easy to do. What is the speed of the satellite? So the speed would be this equation, and I can just say the speed equals the square root of g times the mass of the central body is the Earth over the radius. So the velocity will equal the square root of g 6.67 10 to the negative 11. The mass of the Earth is, just plug it in, 5.97 10 to the 24th over, and okay, now the radius, did I say radius of the Earth? I hope I didn't say that. The radius is the orbital radius. It's the orbital radius. This R is not, even though, okay, yeah, they gave you the radius of the Earth here, but this is the orbital radius that you want to use, how far it is from the center. Now, unfortunately, there's a little bit of math you're going to have to do here for the radius. So let me show you this. Actually, I can do it with the green. All right, I'm going to show you. This, from the white part of this, from the center of the planet, or the moon, the satellite, it's a satellite, I'm sorry. This little part I'm coloring in white is 225,000 meters. But now, the center of the Earth will be the green part. From center of the Earth to the surface of the Earth is 6.36 10 to the 6. You can also write that 6, 3, 6, 1, 2, 3, 4, 5, 6. It will be that far. Is that right? Wait, that seems to be bigger. Oh yeah, it is bigger. It is bigger. So what that tells us is it's not, from here to the center of the Earth is a longer distance. Oh, my picture is kind of out of proportion. 636. 1, 2, 3. Yeah. Let me just read all the picture real quick. Sorry about this. This will make this a little bit more sense why we have to do this on this question. Sometimes, like I told you, when the little girl is standing on the Earth, it doesn't matter that half of her body, we're not counting that as a radius. But look at this problem. This is more like it. Now, this is the Earth, okay? This is better. From here to there, and then the satellite is like right here. The satellite is how far above the Earth? 225,000 meters. But the radius of the Earth is 636 10 to the 6. So I can go 1, 2, 3, 4, 5, 6. So actually, wait, 1, 2, 3, 4, 5, 6. Yeah, this is a lot bigger distance than that is. You see what I mean? So you can't ignore that part. You don't use this radius. You get to use the full radius. This is the orbital radius. Ha! The orbital radius is 225. That's how far it is above the surface there. Okay, but what we need is the full radius. So you got to add it all together from center to center. Okay, here we go. Oh, did I say it wrong? I did say that wrong. This is the height above Earth. The height above Earth plus the Earth radius is green. Height plus the Earth radius is the orbital radius. That's the, I'm sorry for saying that, from center to center. So orbital radius equals 636. If you want to keep it the way it was written there, 6.36 times 10 to the 6 meters, that was the Earth radius, plus 2.25, if you want to do that, or 225, doesn't matter, you can mix them together. 2.25, 10 to the 5th. All right, add those together. So 6.36, 10 to the 6, plus 225,000, and I get 6.58, or 56, times 10 to the 6. So 1, 2, 3, yeah. So see, we significantly changed that to 6.56, 10 to the 6. That is the orbital radius. Wow. All that, just to put that number in here. And now, this times this, divide by that, get the square root, and that will give it to you. So this is actually a shortcut for the problem. We had to go through that long process of finding the orbital radius. Okay? So, that number, 6.5. You know what? It's actually 6.58. I wrote it down wrong. Good grief. Okay. It's 6.58 times 10 to the 6. Or 5.9, really. Well, we'll just go with 5.8. Okay, here we go. 6.67 10 to the negative 11 times 5.97 10 to the 24th equals, and then divided by 6.58 10 to the 6, and then I'll get the square root of that, and it says 7.779. Okay, I'll tell you what, I'll show you the whole math right here with my chalked up calculator. 6.67 10 to the negative 11 times 5.97 10 to the 24th divided by 6.58 10 to the 6, then get the square root of that number, and it's 7.779. So with just 3 sig figs, it could be 7780. 7780 meters per second. That's how fast that satellite is going around the Earth. 7,780 meters per second. And trying to remember, that might be like 3,000 miles per hour or something like that, I think. It's crazy. Okay. All right. So that's the way you do it. Now, part 2 says calculate the period of the satellite. Now, once I have that, there's a couple of other ways to find period as well. Remember when we did the, let me go back and find my notes on it. Which one? Which equation? Not the Kepler's. Let me see. You can just say, oh yeah, velocity is 2 pi r over t. If you want to, v equals, well, you can do that. You can also do this crazy looking equation. I don't know. Well, all right, let's see. 2 pi r over t. Does that fit on there? Barely. 2 pi r over t. You could find the t that way. All right, you could use that equation and do it. Let's do it real quick. Let me just see. So if the velocity is 7780, oh no, actually, it would be 2 pi r divided by v. So 2 times pi times the radius is 6.58, 10 to the 6. Okay, divided by the velocity 7780. And that gives me 5314. Okay, let me try it one more time. If you want to go past this part, you can, but I'll show you why I'm doing this in a minute. It's kind of interesting too, but yeah, 5136 this time. Ha! I must have typed the number in a little bit different. Well, something like that. 5314, 5315, somewhere around there is what I get for the period. Okay, let's see if I get the same answer. Now, what I'm going to do, I'm going to show you the other way to do this, the other equation here. So then you'll know. All right. So it says T equals 2 pi square root of r cubed over GMC. Now, one thing about this nasty looking equation that I like to do, I always tell people, if you're going to use this equation to find the period, go on and do this. There's a radical here, but not here. So let me just go on and square this side and square this side. And look what's going to happen if you do that. This becomes t squared, and that becomes, all right, think about this for a minute. That's like squaring that and squaring that, right? 2 pi squared would be 4 pi squared times just r cubed over GMC. So this equation, if I square it, it becomes this. This part becomes 4 pi squared, but then you just lift up the radical and it becomes that. Maybe it's better to look at that equation and get your answer and then get the square root at the end. So let's plug them in. So 4 pi is 3.14, squared. The radius, there it was 6.58 10 to the 6. But then you got to cube that number. That's why it's just so. I think it's better to take this new equation step. So make that cubed over G is 6.67 10 to the negative 11, and then the mass of the center body, the Earth, is 5.97 10 to the 24th. Wow, what a lot of stuff we have to do here. And then this has parentheses around it, just to be careful with it. But it's a lot better than having the radical in there, I feel like. But let's just see if I can get the answer right. Okay, so 6.58 10 to the 6. Then you're going to cube that number times itself. Divided by 6.67 10 to the negative 11. Divided by 5.97 10 to the 24th. Times 3.14, but it has to be squared. 3.14 times 3.14. Uh-oh. I just messed up my answer. Wait. Okay. We'll see. All right. Now times 4. And I get 305.5. Okay. It looks like I got really close to that same answer, but we'll try it. So I'll try and show you the whole math again, but I'm gonna on my calculator. Okay. Can you see? There's a problem. Yeah, I put it on this side. So first I'm going to put in 6.58 10 to the 6. And I'm going to cube that number. For my calculator, I do x to the y. That means raise it to the third power. And I get that. Now I'm going to divide that number by 6.67 10 to the negative 11. Now I'm going to divide it also by 5.97 10 to the 24th. Now I'm going to multiply it by pi, 3.14, twice. Now I'm going to divide by, multiply by 4. All right, now I get this crazy looking number. 282.16088 is t squared, but then I'm going to get the square root of that number. And the square root I get to be 5312. Okay, it worked. But let me show you something. Okay, so I got 5312 as my period. I did it the short way a moment ago, and I got 5314. And remember, I wasn't sure if that number was exactly right, if I double checked my math. But so they're really close. That's pretty much good enough. You get credit for that. You're within the significance range. But what is the unit for that? It's always in seconds. Isn't that crazy? Remember? 5312 seconds. The period is always in seconds. I think, they didn't give you any other, they gave you nothing else here. So that's how many seconds it is. So now what I'll do is I got to change that from seconds to hours. So 1 hour, 3,600 seconds. Let's just put it in hours. So it's going to be a little over an hour. And that's 1.48 hours. So an hour and a half, and that satellite goes around the Earth. But remember, we were talking about it was moving like 3,000 miles per hour. So this is probably some goofy problem that I just made up. Or if I got it somewhere, otherwise, satellites normally just move, they normally just stay exactly with the Earth's rotation. But 3,000 miles per hour, that would be pretty fast. I mean, if you had a plane that was 3,000 miles per hour, you get around the Earth in an hour and a half. That's what it would tell you here. So yeah, what a crazy problem it was. Now, you might think when you're doing it too, like, why did I do it this way and the other with the period 2 pi r? You know, period is 2 pi r. Because, oh no, I'm sorry. Why did I use the other equation? I already erased it. Well, the reason why I did that is because if this were the only problem you had to do, you'd have to go through and find the other information. So, anyway, you'll see there'll be some case where you have to use this equation. I try to avoid it. If you can ever avoid it, go with the more easy equation if you have that data available. But if you have to use this equation, my advice is to square the t and to square all of that and turn it into this new equation. T squared is 4 pi squared r cubed over GMC. That way, it makes the math a little bit easier. That's the hardest, probably the hardest math equation in the whole chapter that we're doing. Okay, I have done so much. At this point, you probably could almost do the work, but I might have to do, well, let me see. I was thinking about just stopping the video, making a part 2, but let me just try to jump down. Question 3 was how long did it take to move in seconds, minutes, and hours? Well, seconds was given, and I gave you hours. Don't worry about minutes. For minutes, you just multiply the hours times 60. Okay, but let's do letter E. I'll try and go through and finish all. It might be a longer lesson, but maybe I'm going to give you more time to do this lesson then. Another satellite orbits Earth with a period of 12 hours. So here we have Earth again. Well, actually, oh no, I just erased it. Oh well. Okay, so here we go. All right, with a period equal to, what was it? 12 hours. Well, again, just like a problem I just did, when I see 12 hours for a period, I got to go on and put it into seconds. So hour to second, 1 hour, 3,600 seconds. 12 times 3,600 is 43,200. It's got to be. Isn't that strange? You do all these calculations. You got to put the period in seconds. Okay, now it says how high above the Earth's surface is the satellite, and what is the speed of the satellite? Wow! So it goes around in 12 hours. How high above the Earth is the satellite? Okay. Well, first we would also know the thing I erased a moment ago. 636 10 to the 6. Oh, there it was. That's the radius of the Earth right there. And then the height, this time we don't know the height, okay? We know the radius of the Earth. So now we can find the orbital radius using the equation that I showed you a moment ago. And there it is. Well, let's see. If they gave us the period, we could use that nasty looking equation, this one right here. You could say, well, I've got the period, it's, 43,200 seconds. If I plug in the mass of the Earth there, I can find the radius and then subtract to get the height above the Earth. I could do that, how high above the Earth. Or I could also do this, and here's a smart thing to do in physics. Let's just jump down to the next question. What is the speed of the satellite? Oh, look, the speed of the satellite. Oh no, we need to know the orbital radius and the mass of the Earth. No, it looks like there's no way around it. You got to go to that yucky equation. I was about to say maybe we could avoid it somehow. How high above it? Radius, if I know mass of the Earth, I don't know the speed, but I know the period. Okay, well, we got to go to the yucky equation. So here we go again. Okay, so here we go. So I'm going to put the same one I showed you. T squared is 4 pi squared times r cubed over GME of the Earth. Well, MC for central. Okay, and that's your equation. So 43. Now I'm going to have to put that number in and square it. So 43,200. Don't forget, squared is equal to 4 pi squared times the radius cubed, which we don't know, over G, we do know, 6.67, 10 to the negative 11. And we know that the mass of the Earth is, and I erased it from the last problem, but it's up there in D, 597 10 to the 24th. Okay, so here we are. So let's do some math here. So first what I'm going to do is I'm going to say 43,200, and I'm going to square that number. Now I get a really big number. Let's square it. Now I'm going to cross multiply by 667, 10 to the negative 11. That makes it smaller. Also cross multiply 5.97, 10 to 24th. You can do this any way you want. You don't have to do it as I'm doing it. You can do any algebra as you want. Multiply by that, multiply by that. Now I'm going to divide by 4 and divide by pi twice because it's squared. And I get this number, really big number. I get 1.88, 3 sig figs is all I can use here, equals r cubed. Oh, 88, sorry, times 10 to the 22nd equals r cubed. Now, to get the cube root, what you do, some calculators, remember, they have that, but instead, what you can do is just raise that to the 1/3 power. Raise it to the 1/3 power, and that will be r, which is 0.333, you know. So on my calculator, I just go x to the y, take that number, 1.8810 to the 22nd, x to the y, 0.3333, whatever, okay? And you get very big number still. It's 2.66 times 10 to the 1, 2, 3, 4, 5, 6, 7. 10 to the 7th is the radius, and that will be meters. Okay, 2.66 times 10 to the 7th meters. Now, what this has told me is this is the orbital radius. So that's the total, okay? Remember, the orbital radius is the height plus the Earth's radius. So this time, the orbital radius is 2.66 10 to the meters minus the Earth's radius, 6.36 times 10 to the 6, right? And that will give me the height above the Earth. So 2.66 10 to the 7th minus 6.36 10 to the 6, it's going to be 2.02 times 10 to the, it should be 10 to the 7th. Let me double check it. 1, 2, 3, 4, 5, 6, 7. Yeah, 2.02 10 to the 7th meters. That will be the height above the Earth. So the orbital radius, just remember, I don't have the chalk to put there, but the total is the orbital radius from center to center. That's what you just found, orbital radius. And the Earth radius, you got to subtract from that number to find the height it is above Earth, 2.02 10 to the 7th meters. For sure, I'll do some of these in class as well for you. But now that you have that, now what's the speed of the satellite? So if we know the orbital radius, 2.66 10 to the 7th meters is the orbital radius. Okay, now we can use the other equation, and we also know the period was what? 43, it was given 43,200, okay, is the period. And we know from this question a moment ago, 2.66 10 to the 7th is the radius orbital. Orbital period, orbital radius. This long lesson that I'm doing, for sure, this is probably going to be all, like, this will probably be at least, a few days on this one video, because there's a lot of math to do here, and I'll have to go over these in class with you. So, number 2, what is the speed of the satellite? And so the speed uses this equation, velocity, square root of g, mass of the central over the radius. So, g is 6.67, 10 to the negative 11. I'm not putting my units here, I know. I'm kind of just happy to get through the math of this. The mass of the Earth, same thing it's been in all the problems. It is 5.97 10 to the 24th kilogram. And the radius, this has to be the orbital radius, okay? The orbital radius is in this equation. So that's the one that we found out a moment ago, 2.66 10 to the 7th meters. And the velocity will be the square root of all of that. So 6.67 10 to the negative 11, number on the calculator, I'll try to do it here, times 5.97 10 to the 24th. I get that, okay? Now divide by 2.66 10 to the 7th. I get this. So then I got to get the square root of that. Square root of, I don't even like to write this down really. 1496988 I might forget some number. I just leave it in my calculator and push the square root button, and it looks like it's 3,869. 3,869 meter per second. So there it is. And let me try, double check it. 6.67 to the negative 11 times. Yeah, 3869 meter per second. That's your orbital velocity right there. And I might have told you wrong even about the when I was doing the mile per hour. We'll do that in class. When I go over these in class, I'll do that with the Earth's velocity. All right. Well, there it is. So you should be able to do number 5 and 6 on that worksheet. And then if you want to try number 8, you could. There's actually one more you could do somewhere, maybe on an old worksheet, but I'll wait on that. So I might, you know how I sometimes say, well, do this for now, 5 and 6. And then there might be another homework day after I go over it in class, and I'll give you some other problems to do from the same stuff before we move on to something else. All right, I'll see you guys.